perturbative limit from this perspective is actually more subtle than dealing directly with the non-perturbative stuff. But okay, that's how it goes. Okay. And so then if we go to that limit, then delta will be going to some power of epsilon to the n, and that's how we'll read off what we meant by the weak coupling piece of the F theory model. Okay, so this is all just at the level of kind of some nice review of some geometry about elliptic curves and Weierstrass models. Now, what are we going to do to start interpreting this stuff in terms of physics? Is it okay if I erase this? Okay, so in terms of physics, what are we going to do? Like I said, the whole idea in F theory is to geometrize everything we can. So the next step is going to be to say, well, I'm interested in supersymmetric vacua, or more generally, just vacua of string theory, in which I allow this position-dependent axion dilaton to move around in the spacetime. So what would that mean geometrically? It means that we want to consider a spacetime. So I'll write it as R d comma 1 times B. So this is going to be your usual 10-dimensional spacetime. But there's going to be a catch involved. So I'll write the B over here. This could be some high-dimensional space or whatever. Over each point in that B, we're going to now tell you the shape of this elliptic curve. So it could be like this. It could move around. It could be degenerate somewhere. How does a degeneracy occur, by the way? It occurs when we have two of the roots collide. So it can pinch off in some ugly way. So this could be happening. It could be pinching off even more severely. Something like this could happen. Okay? But the basic idea is, if we're interested in the physics associated with this, we say, well, our space-time is this over each point in that space-time. I give you this profile like this. And the reason why I've split B from R d comma 1 is I'm assuming that I have Lorentz invariance in some way in this direction. So in other words, I'm only allowing position dependence in the kind of internal directions of string geometry. So how would we represent this in terms of equations? We would write y squared equals x cubed. Okay, now I'm going to be a little mathematically sloppy here, but I hope nobody minds. I'm just going to write it as f of b x plus g of b. And that's just to encode the fact that as I change b, as I move from point to point, so this is a value of b, there's another value of b, there's another value of b, the values of f and g change. And then what we do is we apply the same algorithm we had before. I go through, I say, at this point of b, this is what f is, this is what g is, and then I go back and I say, this is the value of g. And that tells me the shape of the elliptic curve. And therefore, the value of the string coupling constant at that particular point in my 10D spacetime. Okay, now that prescription is...
Sorry, just an idea to the main question. There is also a story with ATS instead of Minkowski.
Sort of. So I'm going to be focusing on cases where we have just the thing defined in flat spacetime. Now, you can do this in the context of ADS spaces. One of the things that happens there is that you then have to talk about flux backgrounds. And there, this geometric perspective still tells you quite a bit of information, but it needs to be generalized slightly, because you also have to talk about the profiles of all the different potentials switched on. So if you like, the key idea here is that I'm talking about the potential associated with C0.
Indeed.
And if we start talking about the more general flux backgrounds, then you can indeed start switching things around a little bit more. Now, having said that,
it's not well explored.
it's been explored in some papers. So the paper I was most excited about recently was a paper by Martucci, I think, and some friends, where they talk about possibly generalizing away from just the T2 to some higher genus Riemann surface. And the idea is that the other periods of this higher genus Riemann surface tell you about the other potentials. Now, it's not totally clear to me whether that's the most general geometric thing you want to be able to say. But that's kind of the spirit of it.
Okay.
But another approach, which is very common, is that you basically work in a limit where it looks approximately like that flat space, and then you start perturbing away from it through some, by adding a large number of B3 branes at a single point, and you start producing valid perspective on a lot of these things. So, yeah. Okay, thanks. Yeah. Yeah.
So if f and g are continuous functions only, are continuous only, then the fact that you are working modulo SL to Z, already when you specify f and g, because they give you the J function, which is SL to Z invariant, does that mean does not allow you to introduce monodromy, SL to Z monodromy?
Well, in some sense, the SL2, the whole point here is that the SL2Z is really a gauge redundancy. So,
but it can have monodromy.
Absolutely.
That's what I'm asking.
Yeah, I'll come to examples where you'll see the monodromy showing up in the value of tau. So this is still totally allowed by everything I've said.
Yeah. No, I'm just saying, are you allowing this extra thing?
Yes, there will be monodromies if you look at the precise value of tau. Like there will be branch cuts. So if you say, I want tau to be this value, and you go around and come back to the same point, tau will have changed.
No, but you are not working at the level of tau, right? This f and g already give you J. That's what I'm asking.
Yeah, don't worry. I'm going to give you an example where you'll see that if you try and work directly in terms of tau, you're going to see a monodromy show up. So you can certainly do that, and it is a useful perspective for some things.
So f1 to g are simplified.
Well, more precisely, there's sections of appropriate bundles defined over the base B. But yes, if you like it at the most practical level, these are just some polynomials built out of coordinates associated with the B's. So I tell you these B's. Now, these polynomials are not arbitrary, by the way, because if we want to impose various conditions like supersymmetry, these are not going to be completely arbitrary. It's not going to be like you get to tell me your favorite F's and G's. They're going to be forced on you by supersymmetry. But yeah, so at a very practical level, they're going to be just some polynomials. Okay, so the slight subtlety with this is that sometimes you may not even be able to define what you mean by J. This definition of J is actually best suited when the curve has not degenerated in some way. So when the roots of this cubic haven't collided against each other. There can be something singular that happens in the geometry if, say, so I drew it kind of sketchily here. Let me draw it again, a little bit bigger. Let's say that two of the roots hit each other. So that would be an example of like a pinching off in some way. What happens then? Well, by definition of our discriminant, that means that delta equals 0. So this is what's known as the discriminant locus of the F30 model. It's the places where something singular is happening. And if we're physicists, we know that if something singular is happening, something interesting is probably going to be happening at the level of the physical theory. And that's going to be exactly right. At delta equals 0, we're going to find the key players in F theory, namely 7 bricks. So this is delta equals 0 is known as the discriminant locus. Now, more precisely, this thing is going to be some general, so delta equals 4f cubed plus 27g squared. So if I write this as a function of b, what you're actually going to have is some complex equation cutting out some subspace inside of b, or something like that. Okay, so in general, delta could have different components. So along each of these, so I'll call delta I equals 0. So this is what's called an irreducible component. Each of these irreducible components is going to be associated with something that we want to call a 7 brane. Why am I calling it a 7 brane? Well, if we look at how many constraints this thing imposes, it imposes one complex constraint in a 10D spacetime. So it fills out 8 spacetime directions. It's the same as a 7 brane. So this is what is meant in F theory by talking about a 7 brane. It's this generalization of the thing we usually talk about in perturbative string theory, meaning like a D7 brane. But now for this possible non-perturbative generalization of what we would mean by a 7 brane to cover these other cases. Okay. Okay, so putting all this together, you can see that there's actually kind of a 12-dimensional geometric perspective lurking in the background, which is telling us about the profile of the axion of dilettante, and therefore also about the profile of things like 7 branes, namely places where things are going singular in the elliptic model. Okay. Any questions about that?
Is there such a thing as 3 roots colliding?
There's 3 roots colliding. I'll tell you about all the different ways that you can get degenerations of the elliptic curve. But I don't think that happens.
So these loci are non-intersecting, non-intersecting.
Well, I mean, I need to be careful because, well, what do you mean non-self-intersecting?
Non-intersecting.
Oh, no. This can intersect this, and we're going to see examples of precisely that.
So what happens at that intersection point?
Oh, it gets more singular.
Three rules polarity.
Well, not, okay. I'll try to explain a little bit more what happens in those cases. It's not quite that, like, the whole thing collapses, but in fact, this roots picture is more just like a guide to what's going on. To really give you a more accurate picture, you should actually draw pictures like, as funny as it looks, like these little flowers. So, hold on to that question. I may be able to answer it better. Okay. Okay. So far I've just told you about kind of the general picture. Now, what we're going to be interested in the context of supersymmetric conformal field theory is something that has supersymmetry. All right. So how do we demand that? So now let's specialize to supersymmetric vacuum.
Were we talking about vacuum before?
Well, if I tell you, so in other words, it's not totally clear whether I'm talking about vacuum or we keep here.
Yeah.
I'm just telling you a general picture about space-time. Now,
does this axiodilaton have some potential that?
Yeah, so it's set by gravity. So if you consider axion and dilaton coupled to gravity,
Yeah.
you start to produce these things where you have like a curvature in this space, and the profile of the axion and dilaton is actually canceling the effect of that curvature. So an important point about many of these F theory models is that B is not going to typically be Ricci flat. It's not going to be a Calabi-Yau. However, T2 over this thing is going to be Calabi-Yau if we wanted to preserve supersymmetry. Now, a very underexplored area is one where you kind of violate supersymmetry. You try and work out what happens in more detail, those kind of things. Now, trying to solve those differential equations is going to be a nightmare, so I'm not going to do it. Instead, I'm just going to go directly to the supersymmetric case. So that was just like the general background picture. But even in the non-supersymmetric case, this general story I told you is still morally speaking true. You can still talk about things like F's and G's, and you can still talk about things like, not necessarily a holomorphic curve, but you can still talk about the T2 and a torus vibration of some kind. Okay. Okay, so let's say we want supersymmetry. How can we count how many supersymmetries that we have in the system? Okay, I'm going to tell you a shortcut. There's various ways of doing this. I'm going to tell you kind of the maximally lazy way, which I like. We're going to consider F theory on, so let's consider X to be the total space associated with this vibration. So in other words, we have some one-dimensional fibers, the elliptic curves, which might be degenerate and so on at various marked points, marked loci of B. So let's consider F theory on not just X, this is going to be some Calabi-Yau, this is going to turn out to be some Calabi-Yau of B. We're going to consider F theory on T2 times that X. Why is this a helpful thing to do? Well, now I'm going to flip perspectives and consider, instead of F theory on T2 times X, I'm going to consider type 2B string theory on X. Why is that helpful? Well, I just reinterpreted what I meant by the T2. This is just at the level of counting supercharges. So at the level of counting supercharges, there's actually two T2s that I'm talking about. There's one here, and there's one lurking in the fiber of the X. If we flip the roles of these things, then we can just count the number of supercharges involving 2B on this Calabi-Yau. And that will tell us how many supercharges we have in the original F theory model. Why is that? Going down on a T2 doesn't break any supersymmetry. It's a flat. Okay, so this is the maximally lazy way to start counting supersymmetries. There's more sophisticated versions involving just going down on a circle and going to a dual M theory description. But I think this way is lazy. Okay, so let's count supercharges. What can we take? Let's take X to be a T2. take X to be a Calabi-Yau twofold. This is sometimes known as a K3 system. There's not too many of them. 6 dimensions. Take it to be a Calabi-Yau twofold. And the number of supercharges is 32, 16. Basically, the rule of thumb is that as you go down on a appropriate Calabi-Yau, you reduce the number of supercharges you get by a factor of 2 each time. So if we're in type 2B string theory and just flat space, we have 32 real supercharges. If we go down on a Calabi-Yau, we get half of that. Go down again, we get and this is sometimes referred to as the one chiral spinner of 60. Okay. So now the plan for the, when am I supposed to stop? 6 o'clock. Okay, I have time. So now the plan for the rest of the talk is to kind of go through in more detail the vacuum associated to each of these cases. So that's what I'm going to do next. Okay, we've kind of already done the case of 10 dimensions, right? Just to make F and G constants, I tell you a value of the axion dilaton. If I want a Lorentz invariant vacuum, that's it. So that one's good. Any questions about that one? That one's easy. Next case is not so easy. This is more subtle. 8 dimensions. And here we're going to see various things happening. And what we're going to have to specify is polynomials associated with F and G. We're going to have to figure out what the profile of our tau is, or our J function. So let's go straight to, actually, let me keep this. I'm going to get to the. So suppose we now go down to 8 dimensions. Okay, so if we are in 8D, our 10-dimensional spacetime is going to look like R71 times some base B. And this is going to be 1 complex dimension or 2 real, if you like. Depending on how you want to call it. Okay, so let's do the most basic 7 brane. So remember, we're looking for places where things are degenerating in some way. That's what we mean by putting 7 branes into the system. Let's consider the case. So here I'll draw my B again. And let's introduce a local coordinate for this thing. Let's call it little b. Let's try and put a D7 brane, and with the object we know and love from perturbative 2D string theory, put a D7 brane at b equals 0. So let's call that point here. Okay, what do we know about putting a D7 brane in this, just from perturbative 2D string theory? We know that, well, first off, if we look at the world volume theory for this D7 brane, we can think about it as having a coupling to some 8-form potential, which is the magnetic dual of the one associated to the motor-mode 0-form potential. So in equations, we have something that looks like or we do Hodge star in 10 dimensions. Okay, so what does that mean? Well, that means if we take a path around this thing, C0 shifts. Or, if we want to be fancy about it, we say tau goes to tau plus 1. Now, what kind of profile for tau would produce such behavior? If we took tau is equal to even more equations, log of b, this will produce the required behavior. If we send b goes to e to the 2 pi I. We'll just pick up this thing. It'll be a branch cut and put it wherever you want. But if you go all the way around, you'll see this shift. Okay. So that's our tau. What's going on with our J function when we do that? Okay. So I'm demanding that I'm at weak coupling. So remember, we had this J function, and it had this nice Q expansion, plus 744 plus blah, blah, blah. Where Q, I remind you, looks like e exponential of pi I. in the limit where G string is really tiny, I don't care at all about any of this other stuff. It's dominated by this term. Okay, so what I want is I'm looking for something that has this appropriate behavior. And when I want 4f cubed plus 27g squared to be tiny, and this thing to be kind of order 1 thing. So what I'm looking for is 4f cubed plus 27g squared to have the following behavior. It should be order b. Why do I say order b? Well, if I expand this thing out a little bit more, right, q is equal to e to the 2 pi I tau. So I look at this, and I look at this, and then I can see how I'm trying to equate them. I take a logarithm of both sides, and then I can see that there should be this thing behaving as b. Okay, so that's great. That was 1 d7 brain. How about n d7 brains? Well, you do the same thing, but now the shift in the potential is different. The remote Ramon zero form has to shift by more. So the order of vanishing goes up. And that's it. That's the condition. And when you want f and g to be kind of order 1-ish, but you want the discriminant to be such that even though f and g by themselves are order 1, the profiles are tuned such that the discriminant is vanishing like order b to the n. And that n here is tied directly to the number of 7 brains. Okay, now let's say that you put a bunch of 7 brains elsewhere in the geometry. So in addition to this one here, you could now imagine, this was just a local patch. I don't know, they're everywhere on this V thing. Okay. One of the things we have to be careful about is because the 7 brains are so high in dimension, it can cause a back reaction on the whole space-time geometry. And these things carry some tension and with it some stress energy. So we need to be careful that we just put a bunch of d7 brains in here, that if we wanted to say coupled to gravity, we want B to be compact. Gravity. We want this thing to be gravity. We want this thing to be compact. So how can we ensure that we actually globally make an appropriate F-theory model more generally? So this is taking into account the 7 brains. So maybe in the interest of time, I will skip some of that. But the basic idea is that if you allow them to back react, then B needs to be a CD1, and if we introduce homogeneous coordinates for it, let's call them U and B, then the Calabi-Yau condition turns out requiring that F and G have specific degrees. So 8 and 12 is kind of fixed by the condition that you don't that you produce a Calabi-Yau twofold or a K3 surface. I can either leave this as just like a mysterious fact that I threw you, or I can go through it. Which would you prefer? All right, you know, okay. So so to keep things rolling, let me slide over some of that because I want to spend enough time on it.
Can you just say again what the 8 and 12 refer to?
Oh, sorry. They're homogeneous polynomials of degree 8 and 12. So basically, F8 here. Sorry, I should have said that. It is something that looks like UI j, where I plus j is equal to 8, and a similar thing for G12. And delta then has the remarkable property that it's in order 24. It has a degree 24. So this is the statement that there's 24 7 brains in a F-theory compactification of 8 dimensions. Now, having told you that, you're not actually allowed to make things as singular as you might expect. that the types of degenerations of these elliptic fibers over this P1 we classify them. So who classified them? This was done by Kodaira back in let's see, 60s, 50s, something like that. So Kodaira was nice enough to classify all the possible ways you get these degenerations. And so before I tell you the kind of the types of phenomenon you can get, the key point is that the order of vanishing, so F and the order of vanishing for G is bounded. And more precisely, you can't have them both simultaneously vanishing in order 4 and 6. So that's kind of like a 4-6 point, and at that point, the thing has again become too singular. Okay, so what are some examples of kind of nice singular behavior? So basically, at a very crude level, this amounts to an ADE classification of possible degenerations. It's not quite just exactly the same things as the Lincoln diagrams, but it's morally speaking close enough, and definitely close enough in the context of physics. So to give you an example, the one we met already with these D7 rings, these ND7 rings, is what's known as an IN degeneration. And the way that this looks, if you look at the elliptic curve, is the elliptic curve starts pinching off into a necklace. And so what you actually get is kind of the affine A-type diagrams. So you can see that there's an elliptic curve here. But it's squishing off in some ways, degenerating. Okay.
What happens if the order of FNG C is gone?
Then we don't really have a genuine Calabi-Yau threefold. So in other words, this is the statement that the 7 rings have back reacted and have actually destroyed the possibility of the space-time in the first place. So at that point, enough theorists will just say, we're going to encounter actually examples where this happens, but usually the statement is, well, that means that the geometry is actually singular. There's more physics hiding there. Now, if you can resolve that physics and turn it back into a Calabi-Yau threefold through a process, or a Calabi-Yau through a process called blowing up, then you can still interpret it. Then you can say, oh, there's additional physical degrees of freedom. If, however, there's no way to kind of repair the singularity to get back to Calabi-Yau space, then there's just nothing we can say. It just doesn't seem to make sense as an F-linear diagram.
So do they correspond to some kind of metastable vacuum and they decay back to a supersymmetric vacuum in a field theory?
Yeah, I don't know. It might be something like that. The problem with going too high is that what can happen is, so you see this ADE classification. Of course, you could ask, well, why don't I just talk about like, an affine E20 Lincoln diagram, for example.
Right.
I could do that, and I could talk about a gauge theory associated to it. Why don't I do that? Well, if I did that, I would get a non-unitary gauge theory if I then looked at them. And so this would typically mean that there's some kind of non-unitary states that are in the theory, and it's not totally clear what we're talking about anymore. So that's the best I can do in terms of doing a physical interpretation. The kind of conservative answer is, that's nonsense, just don't do it. But if you really try and push it, then that's the potential interpretation of what's going on. Okay, so there's an ADE classification. There's this IN thing. The condition to have this one is that F is order 1, G is order 1, but the discriminant locus is vanishing like order B to the n. That's the condition we just met over there. Now, there's some more examples like this.
Is it like AN of the AD?
Yeah. Yeah.
Okay, fine.
Well, why is it called I sub n? You have to ask me that. I don't know. There must have been a good reason in his head for doing this. In fact, if you go to the physics literature, then depending on how contentious the author is, they'll either say IN